Okay, third video for chapter 11. I just talked about sp hybridization in the simple compound with beryllium. It showed that one of the s orbitals of beryllium kind of mixes with one of its p orbitals to form a different shape that happens to be better at bonding with a neighboring atom, in this case chlorine, to form the best sort of overlap between the two electrons that are localized between them. And again, that hybridization takes on an optimal shape to optimize the degree of overlap in this region between the atoms, essentially strengthening that bond, making the bond as strong as possible. Okay, I'm going to move on then now to another element we don't talk much about, which is boron. Okay, and it's going to be an analogous example here. In fact, I kind of like the picture. I got to redraw. Okay. I'm going to use chlorine again, though, because to be kind of build on the previous example. So the compound that we're going to look at is boron trichloride. Okay, it's kind of analogous to the beryllium dichloride that we saw before. Again, the Lewis structure would show this looking like this. Again, it's not an octet in the middle because boron is electron starved. It's one of the exceptions to the octet rule. Ha ha ha. That's an inside joke. The shape of this is the shape of AX3, which we know is to be trigonal planar. Okay. That's all from V-separ theory. So how does this, or how can we actually explain this using now the VB theory and using the orbitals? Okay. Well, the same kind of thing we did with beryllium, let's look at boron. Boron, again, has, just looking at its valence electrons, it has a 2s orbital and the 3 2p orbitals. And in the atomic version of boron, it fills the 2s and it has 1 electron in the 2p. Okay. Now, when bonding, though, the valence the valence electrons will take on a hybrid orbital in order to bond most efficiently with chlorine. And what happens, just like beryllium, so what happens is that these orbitals hybridize to form 3 orbitals that are a mix and 1 orbital that's empty. The mixed orbitals are known as sp2 because it's a mixture of the s orbital and 2 of the p orbitals. So we take those 3 orbitals and mix them mathematically to produce a set of orbitals that are called sp2 hybrid orbitals. And there were 3 valence electrons and 1 electron fills in each. Okay. Now, let's try to draw this geometrically. Again, there's a better picture than I can probably do in figure 11.3 in your book, but it's pretty analogous to what I did before in that the boron atom in the middle, I guess I'll just draw it like this, wants to bond with 3 chlorine atoms, and what it does is it forms these, that's one, these, let's see, what angle do I want to do here? I guess like this. Ah, shoot. Didn't do the angle right. Right. It's going to form 1, 2, 3. The sp2 orbitals are going to be a combination of, the way I've drawn them, is basically taking the x and the y, basically the plane of the board here, the x and the y, and mixing them with the s, and essentially making 3 orbitals that, again, there's always a little knob in each of these from an electron density standpoint, but I'm going to not include that just for clarity. But the x and the y p orbitals have mixed with the s to form a 3 orbitals that are shaped like this that form a plane. And each of the chloride p orbitals over in the chlorine atom, it's going to have its p orbital, which remember looks like this, overlapping here. And the other chlorine atom is going to have its p orbital overlapping here. And the last one in the same way overlapping here. So that the bonding electrons between boron and chlorine are going to take on this characteristic. They're going to be localized in these three directions in the single plane. Now, if you remember, left over was a p orbital that we didn't hybridize. We hybridized two of the p orbitals with the s to make this triangular shape. There is an additional p orbital left over, which is in the z direction. So it's one of these. It's one of those classic loops in the z direction. Okay, I'm going to try not. I could try to draw it, but I might confuse things. Maybe a different color. I think you can see what I mean, though. So the bonding pairs here between boron and chlorine are forming a nice planar arrangement, basically a triangular planar arrangement. And then there's a p orbital that's looped, looped in the up direction and then in the deep direction. Okay. Now, this actually coincides with our V-separ theory, which shows that BCl3 is an AX3, and it should be trigonal planar. And this model shows that we would agree that it's also trigonal planar. And it has to do with the fact that we hybridize these orbitals to form this triangular, this planar arrangement, with a fourth orbital that's perpendicular. The last p orbital is perpendicular here. Okay? And in some ways that orbital, and this is kind of a hint, is that orbital actually kind of forces the shape. So this is kind of where it should feel a little familiar with the VSEPR theory that shows that the electrons end up kind of forcing by repulsion. They force a certain shape. All right, even though there aren't an extra electrons here, but those orbitals allude to that same behavior. I want to get on to the last one before this video ends, and that is taking this down to its ultimate conclusion, which is hybridizing all of these, or all four of these orbitals. Okay. And we're going to do that with methane. Good old methane, simplest one. You can do it with carbon tet too, but we'll do it with methane. Let's just do it with carbon tet. Carbon tetrachloride. Okay. Now, we remember again from V-separ theory that carbon tetrachloride is a tetrahedral because it follows the AX4 format, and all the bond angles are 109.5 degrees. All right, let's look at carbon from an orbital standpoint. Carbon has 2s and 2p in its valence as its valence electrons, and just the carbon atom we would draw as filling the 2s and having one each in two of the p's. Okay, but in order to form these bonds with chlorine, all four of these orbitals hybridize to form four orbitals that we call sp3. And carbon will have enough electrons to half fill all four of those orbitals. Okay. So what this means then, boy, this will be hard for me to draw, but the carbon in the center will have all four. Sorry. How will I draw this? Good question. Yeah. It's not going to look in the three. There's four of them. It's shaped like a tetrahedral. That's all I can tell you, is that the carbon will actually have 1, 2, 3, 4 orbitals. When the 2s and the 2p mix, they make four orbitals of sp3 that are all symmetric with each other, And that symmetry that they choose is the perfect tetrahedral shape. So these four orbitals will each have an electron, and the chlorines will overlap. This is the chlorine 1, this is the chlorine 2, and you can kind of see the rest. I'm mixing it up here. But essentially these bonding regions that I'm denoting here is the spot where the sp3 orbital of carbon is overlapping, end-to-end overlapping, with one of the p orbitals from chlorine. Okay, so the chlorine valence electron is in that p, and it has a shape that will overlap pretty well with the sp3 orbital end-to-end. And this is why carbon tet has a tetrahedral shape, and this is how we explain it using our modified orbitals that have been hybridized. Okay, that's all I'm going to do for that. But to summarize here is that what I've shown here in this video and the previous one is that the s and the p orbitals can be hybridized, can be combined to explain the bonding between the central atom and either 2, 3, or 4 different atoms. Okay. Okay, I'm going to go on. In the next video, I'll talk about the 5 and the 6, and we'll talk about some other ramifications of this particular theory, the VB theory.